Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. So today we're going to discuss on chapter 5, which is the data link layer. So this will be the last chapter that you're going to learn in this semester, and also this will be the last the 14 weeks before your study week. So in this chapter 5, we're going to discuss on data link layer. So the data link layer is the protocol layer in a program that handles the moving of data into and out of a physical link in a network. Data bits are encoded, decoded, and organized in this data link layer before they are transported as frames between two adjacent nodes on the LAN or WAN. So like this, between these two nodes. And the data link layer also determines how device recover from collision that may occur when nodes attempt to send frame at the same time. The data link layer has two sublayers. The first sublayer is the logical link control (LLC) sublayer, and the second is the media access control (MAC) sublayer. So there are few services that are offered by the data link layer. The first are the frame and link access, which almost all link layer protocol encapsulate each network layer datagram within a link layer frame before transmission onto the link. It also offers reliable delivery. When a link layer protocol provides reliable delivery service, it guarantees to move each network layer datagram across the link without error. And also it provides flow control. So the nodes on each side of a link have limited amount of frame buffering capacity. So without flow control, the receiver buffer can overflow and the frame can get lost. And lastly, it offers error detection and error correction. And this will be we are going to discuss it later in this slide. So I did mention before we have two sublayer in data link layer, which is LLC and MAC sublayer. So the data link layer functionality is usually split into two logical sublayer. So the upper sublayer is the LLC that interacts with the network layer above, and the lower sublayer, which is the MAC layer. And the MAC layer interact with the physical layer below, as shown in this diagram here. So the LLC is responsible for handling multiple layer 3 protocol, which is the multiplexing and demultiplexing, and link service like reliable and flow control. However, and moreover, the MAC layer responsible for framing and media access control for broadcast media. These two. So this basically is the overview of LLC and MAC sublayer over here. These are the components, the main components in the data link layer, which is the adapter or NIC, network interface card. So for a given communication link, the link layer protocol is for the most part implemented in this adapter NIC. So every computer, whether it's wireless or wired using LAN, it has a NIC, network interface card. So what's the function of NIC? The adapter encapsulates the datagram in a frame and then transmit the frame into the communication link. At the other side, the receiving adapter receives the entire frame, extract the network layer datagram and pass it to the network layer. So that is the function of the NIC. So in the NIC or the adapter card, it has two components, which is the bus interface and the link interface. So the bus interface is responsible for communicating with the adapter parents node. It transfer data and control information between the nodes and NIC. And the link interface, which is this one, is responsible for implementing the link layer protocol. In addition to framing and deframing datagram, it may provide error detection, random access, and other link layer function, which is for the MAC sub layer. So let's look into the error detection technique in data link layer. So we're going to discuss these three error detection techniques. First is parity check, second is checksum, and third is the cyclic redundancy check. So let's look into the parity check. So this is the simplest error detection techniques that is being used in the data link layer. So for example, we have this D data bit. D is the number of data bit. So what happens is if an odd number of one value bit here is found, so the parity bit will be 1. If it's even numbers of one value bit over here in this data bit, the parity bit will be 0. So that's how the parity check work. So how they detect the error? If the parity bit is 1, however, the bit here has, for example, the number of one value bit is suddenly become even, so means that this data bit has error. So that's how the parity check works. However, with this parity check, it can only detect the error without any correction done. So let's look into this two-dimensional parity check scheme. So with this two-dimensional parity check scheme, we can not only detect the error, but we can do the correction. For example, if you look at this, if we have this is the parity bit and this also the parity bit. So if you look at here, we have 3 numbers of 1 bit value, so that's why parity is equal to 1. And over here we have 4 value numbers of 1 bit, so we have an even number, so that's why we got 0. On top here it is even, that's why we get 1. So from this here we know that this has no error for these all data bits. However, if you look at this part here, maybe this will be the sending data bit and this is the receiving data bit. So if you look at it here, this bit here has an error. Basically it should be 1, but it becomes 0. So how the receiving side detect the error is by checking the parity bit. So the parity bit is here is 0, so it should be an even number of 1 bits, value bits. However, it has 3, so it is an odd number of 1 value bits. And over here is also checking the error. So we know by crossing these two parity bit, we know that this bit here has an error. So that's how this two-dimensional parity check scheme is working. So let's look into the checksum. Basically, it's the same as we discussed in the transport layer protocol in chapter 3. So you can look back how the checksum work. And lastly, the cyclic redundancy check, CRC. So this is an error detection technique used widely in today's computer network. It's also known as polynomial codes. So CRC are so called because the check or the data verification value is redundancy. They expand the message without adding information, and the algorithm is based on cyclic code. So the CRC are popular because they are simple to implement in binary hardware, easy to analyze mathematically, and particularly good at detecting common error caused by noise in transmission channel. Let's look into this example. For example, we have a D bit of data 101110, and this is the divisor, which is G. So the first thing that you need to do is to generate the CRC is a string of n zeros is appended to the data unit that is going to be transmitted, which is this one 000y. We have 3 bits of 0 because over here we have 4 bits, so we need to add 4 minus 1, that's why we get 3. And then the binary division is performed of the resultant string with the CRC generator. So this is going to generate the CRC. So basically after the division, the remainder of the division is so called the CRC, which is R here. So the packet or the datagram that is being sent will be the D bit of data, D, and also the R, which is the CRC bit. Okay, let's look into the multiple access protocol for broadcast. So there are two types of network link. First is point-to-point link, which is from one host to another host, and broadcast link, which is from single host to multiple hosts. So the internet is probably the most widely deployed broadcast link technology. So broadcast channels are often used in local area network. Now they are geographically concentrated in a single building, for example, a corporate or university campus. Thus, we'll also look at how multiple access channels are used in the LAN. So nevertheless, we can classify just about any multiple access protocol as belong to one of the two categories. So the first is the channel partitioning protocol, and the second is the random access protocol. So this is example of the shared wired network using RJ45 cable, and this is the shared wireless using wireless LAN. So let's look into the channel partitioning protocol. So the time division multiplexing, TDM, and FDM, frequency division multiplexing, are the two techniques that can be used to partition a broadcast channel bandwidth among all nodes sharing in the channel. So as an example, suppose the channel support n nodes and that the transmission rate of the channel is R bit per second. So TDM divides time into time frame and further divide each time frame into n times slots. So each slot's time is then assigned to one of the n nodes. So it depends on the time. So each host has its time slot. So whenever a node as a frame to send. It transmits the frame bits during its assigned time slot in the revolving TDM frame. So while TDM sharing the broadcast channel in time, FDM divides the R bit per second channel into different frequency, so each with a different bandwidth, and assign each frequency to one of the nodes. So this example is the FDM. So if you look at this, the y-axis here is the frequency, and this is the time. The x-axis is time. So at this frequency, you can see that it divides the channel into different frequency with fixed bandwidth. For example, each frequency has 4 kHz bandwidth. So each host is assigned with different frequency. However, in TDM, if you look at this example, it has 4 hosts basically, and each host has its slots, time slot. We call it time slots. For example, if a sender wants to send to a host 2, so we need to wait for the time slot here to send the data, and it repeats on and on again. So if it has 30 hosts, so it has 30 slots, and then it repeat it again, and so on. So let's look into the random access protocol. So the second broad class of multiple access protocol are so-called random access protocol. In a random access protocol, a transmitting node always transmits at the full rate of the channel, namely R bit per second. When there is a collision, each node involved in the collision repeatedly transmits its frame until the frame gets through without a collision. But when a node experiences a collision, it does not necessarily transmit the frame right away. Instead, it waits a random delay before retransmitting the frame. The random access protocol is further divided into 4 categories, which are Aloha, CSMA, CSMA-CD, and CSMA-CA. In this chapter, I'm just going to discuss the Aloha and CSMA. So let's look into the Aloha protocol. So the Aloha protocol, or also known as the Aloha method, is a simple communication scheme in which every transmitting station or source in a network will send the data whenever a frame is available for transmission. So if we succeed and the frame reach its destination, then the next frame is lined up for transmission. So this has no slot or anything, just randomly transmit. So but remember, if the data frame is not received by the receiver, maybe due to collision or packet loss, then the frame is sent again until it successfully reaches the receiving end. So to avoid the collision, so the slotted Aloha was developed. So basically, the slotted Aloha is to minimize the collision and to optimize network efficiency, as well as to increase the number of subscribers that can use in a given network. So the system consists of signal termed as beacon, which are sent at precise time interval and inform each source when the channel is clear to send the frame. So basically, the beacon give a slot to any source or sender that want to send a frame or a data frame. So let's look into the CSMA. CSMA stands for Carrier Sense Multiple Access, which is nowadays used in the Ethernet protocol. So till now we have understood that when 2 or more stations start sending data, then a collision occurs. So With CSMA method, it can decrease the chance of collision when two or more stations start sending their signal over the data link layer. So basically, how do they do it? So the CSMA makes each station to first check the medium, whether it's busy or not, before sending any packet. So basically, all the station or the host, the sender, has capable to sense whether the what we call the medium or the communication, the network is available or free or not. So whether whether it's free, it will sense if it sends, for example, B sends the network is free without any packet or frame, it will send the data frame into the network. So let's look into the Ethernet. There are many reasons for Ethernet success. First, Ethernet was the first widely deployed high-speed LAN. Because it was deployed early, network administrators become intimately familiar with Ethernet, its wonder and its quirk, and were reluctant to switch over to other LAN technology when they came on scene. So an Internet LAN can have a bus topology or star topology. However, currently we are most of network use star topology. An Ethernet LAN can run over coaxial cable, twisted pair copper wire, or fiber optics. So for economic costs, most of the network use coaxial cable RJ45. And furthermore, Ethernet can transmit data at different rates, specifically at 10 megabit per second, 100 megabit per second, or 1 gigabit per second, depends on the medium use. For example, coaxial cable can go up to 1 gigabit per second. If it use fiber optic cable, it can go higher, maybe 100 gigabits per second. So this is the Ethernet frame structure. It has a preamble, destination address, source address, data, and CRC. So CRC is the error detection and error correction bit. So Ethernet use baseband transmission. That is, the adapter send a digital signal directly into the broadcast channel. So the reason for Manchester encoding is that the clock in the sending and receiving data are not perfectly synchronized. By including a transition in the middle of each bit, the receiving host can synchronize its clock to that of the sending host. Once the receiving adapter clock is synchronized, then the receiver can delineate each bit and determine whether it is 1 or 0. So this is basically the Manchester coding. So for example, the bit stream or the data is 1010100001, and the binary encoding is this one. So the Manchester encoding will translate is, if it's 1, the Manchester encoding translate from 1 to 0. If it's 0, 1 to 0, 0 to 1. If it's 0 again, 0 to 1, 0, 0 to 1, and if it's 1, 1 to 0. This is how the Manchester codings works. So that's all for this chapter. Hope you familiar with the data link layer, and this will be the last slide for this semester. So I hope and wish you good luck for your final exam. Assalamualaikum warahmatullahi wabarakatuh and good afternoon.